How you doing, physics fans? We're going to talk about the basics of circuits today, and we are going to look at just what goes in it a little bit and try and keep it mostly pretty simple. So let's get to it. This is pretty much the most basic circuit you can have. You've got just a battery and a resistor. So the battery has an EMF I've written as epsilon, and then you can do things like apply Ohm's Law to this. So I can say that the voltage drop across the resistor is equal to the current through that resistor times resistance, times its resistance. So I don't know, I made that capital. So that's Ohm's Law. And you can write it in different forms too. So now Ohm's Law, if you remember, is more is better as a definition of resistance than a law, because it turns out that these guys, it doesn't always work quite like this, right? Because your resistance can be affected by current or temperature or things like that. So it's better to say that, and so like if I can't say this resistor has a resistance of 10 ohms. So it's better to more describe it as resistance is defined by the ratio of voltage over current. So in that way, it's a little more clear what's going on, I think. Okay, so then what do we do if I have parallel resistors? How do I do that? Or not parallel, I'm sorry, series resistors. So let's go ahead and draw that. So there's our circuit, poorly drawn as always. So the effective resistance of our resistors for a series circuit is just going to be the sum of those two. So that's going to be R1 plus R2. Oh, I want to go back to my battery for a minute and talk about which end's the positive and which one's the negative. So this end's the positive and this one's the negative. Why'd they pick it that way? I don't know, because it's the opposite way that it is on a AA or a AAA battery, and that's really annoying. Because I just remember it as the opposite of a real battery. It's so stupid. Okay, so then how much current flows through my circuit here? Well, if I want to do that, what I could do then is I would say I find my effective resistance is R1 plus R2, and I know the EMF of the battery is that. I could then say current is equal to V over R, which is going to be EMF over R1 plus R2. Now, how would you measure current, though? Well, I'd want to put an ammeter right here. I'm going to mark it with an A for ammeter. And I'm going to put it in series in my circuit because I want all of my current to pass through my ammeter. So I'm going to say ammeter goes in series. What if I had two parallel resistors? Let's go ahead and slide the paper. And let's draw that. So if parallel resistors look like this, now the first thing we should ask ourselves is, how do we know if it's in parallel or if it's in series? Well, parallel is the one that people a little bit tripped up on sometimes. It's in parallel if the current has a choice. So the electrons are leaving this negative end of the battery, they come this way, and then it has a choice. Do I want to pass through this resistor or do I want to pass through this resistor? And then it joins back up and goes to the battery. It cannot flow through both resistors. So the current must flow through only one of the two. So let me clarify what I just said. Each electron can only pass through one of the two. The current actually passes through both, because the current is going to come here and choose. Now, because the current is made up of many, many electrons, huge, absurd numbers of electrons, because they are tiny. So the current is going to pass through both, but each electron has to choose. So in our example up here, one thing we should probably ask ourselves is, what is the potential difference across each of these resistors, R1 and R2? And so for potential difference, what I'm going to say is the current through both of these resistors is the same. So the current is the same in both resistors, but the potential difference, the PD, is different. So how do we find that? Well, to find the current, we did that a second ago. Now to find the potential difference for each resistor, I'm kind of out of space up here, so I'm going to just come down below and maybe right above. So I can say if I want the potential difference for one, I would take the current through 1, which is the same as the current through 2. So I could just write I, if I want to, times R1. So then if I wanted to write everything out, I can take this value and put it in here for the current and say it's going to be epsilon R1 over R1 plus R2. And the current in resistor 2 would be the same thing, but this right here would be a 2. R2. All right, back to parallel resistors. So the current passes through both resistors. What's the potential difference across both resistors? Well, since if we follow each path separately, because the electrons have to be back at 0 volts when they come back to the battery, then it must lose the whole potential difference of the battery in the resistor. So that's not a general law, of course, because if I put, say, a resistor here and put one, so it would have to lose some here, or if I put a resistor here, it would have to lose some here. So it's not going to just drop the whole voltage across these resistors, because there are other places that could lose some. But a more generalized phrase I could say is the potential difference across each parallel path is the same. So how do we find the current in each resistor now? To do that, I need to know it's actually going to split in proportion to the ratios of the resistance, and it's going to prefer the path of least resistance. So now to say it favors it, though, got off the screen a little bit. To say it favors the path of least resistance, though, does not mean it only chooses that. It takes both, but it's going to be stronger in the path of least resistance, more current there. So to find the current, I need so what I want to do is, since the potential difference is the same in both, right? I can say, so first the step would be find the potential difference. So let's say how to find current. So your first step in that is going to be find the potential difference of your parallel resistors. And then your second step is going to be to use Ohm's law. Since you know the potential difference now, you can say the current is going to be that potential difference divided by the resistance. So if I wanted to know the current through resistor 1, that would be the potential difference across 1 divided by the resistance of that first path. Sound good? All right, let's move on. I guess one thing we should have talked about is how to find the potential difference of the parallel resistors if I had something else. So imagine I had a more complicated circuit, one that looks like, there it is. So I want to know how do you find the potential difference across this? Well, to do that, I would want to add the two resistors and find the effective resistance. Now for parallel resistors, the effective resistance, you're not going to do it the same way, because before I just said let's add them up. But for parallel resistors, I'm actually going to say 1 over the effective resistance. It's going to be 1 over R1 plus 1 over R2. And if I had any more in another branch, it would be plus 1 over R3. So it's best to think about this, I think, like traffic. Even if if you have more roads connecting a place, it's going to be easier to get there. Even if one of these roads is giving you the same amount of traffic, right, and the same amount of force pushing people through. Even if one of these roads is real crappy or small or has a lot of traffic lights, it still alleviates some of the demand for this bigger road. Okay, so what's my effective resistance here? Well, in this case, I'm going to say 1 over effective resistance is going to be 1 over 2 plus 1 over 6. And that is going to add up to 4 over 6. So my effective resistance is going to be 1.5 ohms, because I'm just going to flip that, right? Okay, so then now I don't know the current passing through it is, right? How do I find the current passing through it? Well, my total effective resistance, so maybe I should call this RF parallel. Our total is going to be, that's a 1.5, I don't know if you guys can tell, 1.5 ohms plus 1.5 ohms, right? So that's going to be 3 ohms. Is going to be total. So the total current passing through this whole thing, it can be found using this value. So what I like to do after I draw this is I like to simplify my circuits, because to me it helps me visualize. So now I know I have 1.5 ohms here, I have 1.5 ohms here. If I want to simplify this again, it would just go to one resistor. Ooh, I meant to make that smaller. Oh, you guys can't see what where I'm drawing now. And that's going to be 3 ohms. And so now I can say, well, how do I find the current here? Well, we did that before. It's going to be V over R is current. So my current here, in this case, given this was 12 volts, is now going to be 4 amps. Let's get some more paper. So the next step is to figure out what's the potential difference across each resistor. So if I say I put a voltmeter here, one thing we should note is that voltmeters go in parallel. I could measure that potential difference, or I can calculate it since I know everything about the circuit, right? Because that's still 12 volts. So to calculate it, first of all, it's an easy one because I know they're the same. So I could just in my head say it's going to be half. But if I wanted to do it, be fair about it, I can say V equals IR. And I know that the same current passes through this effective resistor. And I'm considering effective resistors, not individual right now, and this resistor. So that means I can find the potential difference across this resistor, which remember will be the same for this one and that one, using Ohm's law. So I can say V equals IR, and then I can say my current is 4 amps, and then my resistance is 1.5 ohms. Ooh, ohms. Made it work. And so that is going to be 6 volts. My mistake. So which is half of 12, like we said earlier. So now if I want to find the current through each of these resistors here, I know I can use my Ohm's law, right? So I can say the current through the 2 ohms, I'm going to call it I2, is going to be V2 or V parallel or whatever you want to call it. Let's call it V parallel over R2. So that's going to be 6 volts over 2 ohms. So that is going to be 3 amps. And the current through, we'll say resistors, call it 6 because it's got 6 ohms. It's going to be V parallel over R6. So that's going to be 6 volts over 6 ohms, which is 1 amp. And you will notice that these values are going to add up to 4 because they should add to the total, because I have to be conserving charge and I can't just let the electrons wander off into nowhere. There's nowhere for them to go. It has to pass through this resistor. So now I know the current through this resistor, through that one, through this one, and the potential difference across all of them. So I think we've pretty much solved that circuit unless we want to do power. But since this is a 13.5-minute video already, that sounds like a video for another day.